Hi everyone, I'm excited to welcome you to today's webinar, Reduce Autonomous Vehicle Sensor Blindness with the Moving Particle Simulation Method. My name is Karen and I'll be hosting today's webinar. So we have talked about the MPS solution ParticleWorks in a few webinars before, each demonstrating the different uses of ParticleWorks and its capabilities of understanding fluid flow. In this webinar, we will focus on ParticleWorks to understand the effect of vehicle soiling and how to reduce sensor blindness. Today, it will be our senior project engineer, David Percival, who will take us through the ParticleWorks webinar. David, would you like to introduce yourself?
Thank you, Karen. So my name is David Percival. I'm a Senior Project Engineer for EngineSoft UK, and I am the UK lead for ParticleWorks. So whether it's a consultancy project, a training, a methods development piece, or just a software sale, you'll probably be dealing with me in some way or another. So my background is actually in mathematics. I did a master's degree in maths specialising in fluid dynamics, which is how I've got into computational fluid dynamics. But fear not, we're not going to go too much into the details of the maths behind ParticleWorks today. We're just going to be focusing on what the methodology is and how it can be used to simulate vehicle soiling. Thank you very much.
Thank you, David. Before we get started, I would just like to remind everybody that you are just muted for the efficiency of today's webinar. But if you have any questions throughout, please feel free to use the chat box. We'll endeavour to cover as many questions as we can at the end of the webinar's Q&A section. So back to you, David.
Thank you very much, Karen. So hopefully everyone can see my screen now. I just wanted to go through a brief introduction to the MPS method and what it is and how it differs to conventional CFD before we get into the case study. So first of all, what is the moving particle simulation method and how does it relate to ParticleWorks? Well, the MPS method is essentially the engine behind ParticleWorks. It's what calculates the fluid's motion, velocity, pressure, anything else that we want to look at in ParticleWorks. Now, ParticleWorks is the only tool on the market that actually uses the MPS method. There are other particle-based CFD tools on the market. However, the MPS method is the only tool which was specifically designed for simulation of incompressible fluids such as water or oil. There are other tools on the market for particle-based simulation. However, these are not designed for simulating incompressible fluids, but instead compressible fluids, some of which have been adapted to work with incompressible fluids, but they're not their primary directive. So, going back to the MPS method, I want to give, first of all, a very brief overview of its main features. So first of all, no mesh generation. Now for those of you who have worked with traditional CFD in the past, you will know how long a step this can be in the simulation process, often taking even longer than the simulation itself. Before we start a particle simulation, there's no meshing to concern ourselves with, we're just getting straight into the simulation right from the get-go. I'll talk a bit more about this, why this is on a later slide, but ParticleWorks is best suited for simulating anything with a splashing element or a free surface flow. And in relation to conventional mesh-based CFD, it's far faster and far more accurate than we would ever get with a mesh-based simulation. Again, due to the lack of a mesh, moving boundaries are much easier to deal with. We don't have to worry about things like mesh deformation, mesh overlap, and overall it's just a much simpler methodology to deal with anything where there's a moving part involved. And then finally, we have a nice feature in ParticleWorks called the coarse graining model. This allows us to simulate very fine particles using a much larger particle size to save on computational time. So this allows us to simulate the effect of very small particles without the requirement of actually using tiny particles. And we'll see why that's beneficial, especially for vehicle soiling in a little bit. So, in terms of the physics, well, the equations that we're solving in the MPS method is exactly the same as what we're solving in the conventional method. The only question is, how do we solve it? So, in traditional mesh-based CFD, we are taking the Eulerian approach of solving the Navier-Stokes equation. What this means is that we are solving from a fixed outside point of view on the nodes of the mesh. However, in the MPS method, we're still solving the Navier-Stokes equation, but we're taking the Lagrangian approach and solving from the point of view of the particles. This essentially means that the particles act kind of like a moving mesh, and they move where we need to do the computation, so we're not wasting any computational time anywhere else. So that becomes clear in this, this very simple water column collapse example. So in the conventional method, you see that initially we have the fluid in this blue block on the left-hand side. However, at every single time step, we are solving on all of these nodes. And in this white region, we don't really care what's going on right now. The fluid's not there, we're not interested, so we are wasting computational time. Now in the MPS method, there's no waste of computational time, we are only simulating where the fluid actually is. As the water column collapses and we see the fluid body evolve and move, we struggle to capture that free surface in the conventional method. The reason being that we don't have a fine mesh everywhere. If we were to have a fine mesh everywhere, then yes, we could capture that free surface accurately, but it means the simulation time would be astronomical. Now in the MPS method, we're capturing that free surface at the same resolution everywhere, regardless if we knew it was going to evolve to this position or not. So what you can see here, as it's collapsed, it splashed into this right-hand wall and come up and out of the box. Now we're still capturing that at the same resolution as everywhere else, even though we didn't know that it was going to go out there beforehand. So in the conventional method, we might not have meshed in that region, so that means that the information is lost and we're simply not getting any results for the fluid behaviour in that area. So much faster overall and far more accurate than we can ever achieve for this type of simulation. So let's jump into the case study then. So before we actually get onto the case study, I want to just talk a little bit about what the problem is that we're trying to solve and why Particle Works is the best tool for this job. So first of all, as modern cars have ever more advanced driver assistance systems, and we have more and more sensors, and ultimately we're pushing towards fully autonomous vehicles, it's of critical importance that we can ensure that those sensors are able to see for all possible driving conditions, no matter what the world might throw at us. Now, if the sensor can't see, then the car isn't able to adjust the driving, see hazards coming, and ultimately this puts the passenger's safety at risk. Obviously, we want to avoid this at all possible costs. Now, physical testing is great, however, this is such a complex problem that actually controlling how the soiling is coming into the vehicle and being able to test all the different potential scenarios is basically impossible using physical testing alone. And regardless of how much we're able to do in physical testing and how much we're actually able to monitor what effect that has on the sensors, well, the insights that we are able to gain are reached far too late in the design process. We're only able to actually do physical testing once the parts have been committed and we have started manufacturing and we have a physical thing we can test. Designs are locked in at this point and there is very little we're actually able to change if there's even any time or budget left to change them. This means we need to use instead simulation. Mesh-based CFD, however, is not well suited to this sort of application. As we've already discussed, this is a highly complex system with moving parts, splashing elements and free surfaces. So in order to actually be able to simulate this in anything like a reasonable time frame, it would need to be such a coarse simulation that it's not going to reflect reality at all. So in order to have an accurate simulation, we may be able to get one simulation done if we start it right at the beginning of the design process, which again is nothing more than a verification test, whether or not the design is going to work. But then it's too late to do any iterations, and we wouldn't even be able to do any iterations in the virtual world anyway using mesh-based CFD. So all that leaves us is a particle-based CFD tool, such as Particle Works using the MPS method. Now this is able to bring valuable insights right at the start of the design process, and we can then start using that insight into understanding what the initial soiling state is and how can we improve upon that. The simulation times of these applications are of such a short time period that we're able to do numerous iterations on every single countermeasure such that we're able to fully optimize the performance and get the best possible design we can. So, over the course of the next 20 minutes or so, I'm going to be trying to demonstrate how Particle Works can answer the following questions. So firstly, how quickly do the sensors get occluded? How quickly do we lose vision of those sensors due to the driving conditions and the contaminants on the road? Now that we understand how quickly they do get dirty, what can we do to prevent that? Can we introduce passive or even active solutions to try to mitigate reduce the overall soiling rate and keep the LiDAR cleaner for longer? Now, ultimately, we're never going to be able to get this completely down to zero. There's always going to be some level of occlusion due to the environmental conditions. So when we are dirty, how do we clean that off the sensors so that we are able to see again? And then finally, how quickly and efficiently can we clean the sensors? Well, if it takes us 20 seconds to clean the sensors again, then that means the car is blind for all that time and potentially we are driving into a hazard. Also, if every time we have to run it, we have to use half a litre of fluid and have to refill the fluid washer tank every 5 miles, this is clearly not a very ideal solution, and the pump's going to drain a lot of power from the car, and the operational range of the vehicle is going to be significantly reduced. So overall, can we reduce the time it takes to clean and how much power and fluid it uses to clean those surfaces? So, if we actually get into the actual scenario, first of all, we have our nice generic car here. We've obviously made it EngineSoft branded for the purposes of today, and we can also make it an autonomous vehicle. So, let's throw a couple of these LiDARs on there, and these are the spots that we want to keep clean throughout the rest of the simulation. And there's also 2 on the back here, and we'll take a look at them later on. Now, for the sake of simplicity, we're going to fix the frame of reference to the car. So what that means is that the car stays still, only the tyres move on the car, and then the road moves into the path of the vehicle at whatever the driving speed we've set is. Obviously, as we start introducing air and other contaminants as well, then they are also going to move into the path of the car and not the car move into them. Now, if we want to look at other vehicles as well, this is something that we can include in particle work. So in this case, we've got one lorry up the front here that the car is following, and then a second lorry which is overtaking it. If you want to do other cars as well as lorries, maybe cars travelling in other directions, the car could even be static and being passed by other vehicles. Whatever you want to do, if you can dream it, we can probably build it in particle works. There's obviously a number of different ways that the car can get soiled. So in this case, we've got rainfall. How does that interact with the LiDARs? So especially the ones on the front in this case. Or maybe standing water. So this is going to be more affecting the rear of the car potentially. How does standing water affect the overall soiling rate of the vehicle? Basically, there is a myriad of different conditions that we might want to simulate, and this is one of the challenges of doing it in physical testing, is knowing which one wants to run, and then being able to actually analyse all those scenarios on a test track is going to be near impossible. The sort of things that we might be interested in looking at and that we are able to control in particle works are things like the speed of the vehicle. So for the rest of the videos you're going to be seeing today, the vehicle speed is set to, I believe, around 80 miles per hour. Any other vehicles on the road? So do we have cars travelling in the other direction, same direction? Are we following, being overtaken? What's going on around the car? Again, for simplicity's sake, today we're just going to have the vehicle on its own. What contaminants? So is it water? Maybe the road's being gritted and we've got now a saline solution on the road. Maybe some mud or a combination of mud and water. There's some dust in the air or even potentially snow. Any contaminants, we are able to apply them in particle works as long as we can define them as a fluid or a powder. Then what is the source of the contaminant? So is it standing, like on the road, we're driving through a puddle, for example? Is it falling? So do we have rainfall? Or potentially a combination of both of them, or even suspended in the air. So maybe we're driving through along a dusty road where there is just dust suspended in the air. And then finally, what is the contaminant load? So are we having a heavy rainfall? Is it a deep puddle that we're driving through? All of these are things that we're able to vary within particle works and simulate a number of different driving conditions in a very quick and easy way. If there are other contaminants that you can think of or other scenarios that you would like to have a look at, feel free to ask a question and we will try to get to you in the Q&A at the end. So now we understand the sort of challenges and what we are able to simulate, let's look at how we actually build up that process. Excuse me. So the first step is to calculate the airflow. Arguably this is the most important step because this is what's going to be driving the fluid around the car and causing it to be deposited on different regions on the car. The way that we do this is using the FVM method. Now you might be thinking ParticleWorks is a particle-based solver, not a mesh-based solver. Well, ParticleWorks thankfully has a FVM solver built in specifically for the purpose of calculating airflows, either around an object such as a vehicle or within something like potentially a gearbox or an e-motor. So as we already mentioned, what we're going to be doing is injecting air on the left-hand side here into the path of the vehicle and then seeing how it develops around the back of the car. And we can see this wake forming here, for example. Now, you might be worried about mesh generation. As I promised at the start, you don't have to worry about mesh generation with ParticleWorks. So it seems like I'm telling you porcupines, and you're going to have to pick up the mesh generation again and spend potentially weeks building this for every different design iteration. Well, no, thankfully ParticleWorks is able to generate a uniform Cartesian grid, and the mesh generation takes only minutes and is handled within the pre-process without any engineering input at all. Once we have the airflow, we can then apply that to a fluid analysis. So what we're doing here is we're going to be doing a standing water simulation. So you can just about see at the bottom here, we have an inflow generating particles at the speed that we are driving down the road. We can then see how they interact with the tyre and then subsequently the air, and then how they can get deposited onto the car. So what we can see here, fluid getting injected, getting picked up by the tyre, and then moved around by the airflow. Now the problem that we have here is that in order to keep this simulation time down to a reasonable time frame, we're using 3mm particles in this case. And that's quite a large particle size, and that means the particles are quite heavy and they're not really getting affected by the airflow. Now, from some prior research, we've determined that the particle size that is created, the droplet size of a water droplet ejected by a tyre driving through a puddle wants to be in the range of around 0.6mm. There's nothing stopping us of bringing the particle size down to this size. However, this is going to lead to a massive increase in the number of particles, and also a reduced time step is going to be a lot smaller, meaning the simulation is going to take far longer to run. So what do? We're either having a simulation which is not simulating reality because the droplets are too large and not affected by the airflow, or the simulation takes too long. Well, I've actually already mentioned the solution, but we do have in ParticleWorks the coarse graining model. What this allows us to do is to scale the particle size so that they are reflected by the airflow. So what this means is that the effective mass of the particles is scaled to that of a particle of diameter of 0.6mm, and also the surface the surface area, so that the amount that the airflow affects the particles is also scaled. This allows us to create the effect of the very light particles without the requirement of simulating those small particles, which would take them far longer, and we wouldn't be able to iterate the design nearly as much as we could for these large particles. So what we're seeing here is the particles getting ejected by the tyres. They're getting caught in this wake behind the vehicle and then getting recirculated and deposited onto the rear of the vehicle, and most importantly, onto our LiDAR. So once we have the scaled particle simulation running, we can then look at what the actual deposits look like on the mapping. So what we're seeing here is every time the particle hits this surface, it's creating it's adding a value onto this mapping, and the more frequently a particle hits that specific node, the further up this rainbow we go. So you can see the red region here is where particles are hitting the bumper, draining down and dripping around the outside of the LiDAR. Potentially if we could build some feature here to redirect those drips, and we don't have this red band form anymore. Regardless though, we do still have a very green picture overall, which means quite high soiling for the base state. So we need to do something to improve upon this. Now it's not just pretty pictures that ParticleWorks can generate, we can actually get the data out of this as well. So what I've exported here is the instantaneous and the cumulative mapping, cumulative occlusion for this surface. So what we can see is that instantaneously we're getting anywhere up to around 10 to 15% coverage at any one time step. And overall we're getting full coverage of the 100% occlusion within around 2 seconds of the initial particle hitting this surface. Clearly we need to do something about this. Now, from this image here, it's very hard to determine where the particles are actually coming from, which hits this LiDAR. So it's hard to know what we need to do and where we need to put features in order to try to improve this. We have this handy tool that can help with this in particle works called the path line tool. So what I've generated in this video here is I've taken all the particles which are hitting the LiDAR for a certain time period and then traced them back to see where they originated from. And what we can see is that they are coming up from the rear tyre, or the vast majority of these are coming up from this rear tyre and then coming up underneath the bumper and striking the underside of the LiDAR, which is why we have such high coverage. If I can get my mouse back, you see such high coverage, especially on the underside more than the top side. With this in mind, we can start to hypothesize what might work for countermeasures to try to reduce the overall soiling rates. So this is our initial car. Then what happens if we put in some mudguards? Clearly this isn't the prettiest feature, and I don't think the design guys are going to approve this new feature, but we can prove it in principle whether or not it does help us, and then we can iterate the design to get something that looks a little bit nicer but still is performing well at this scenario. So once we have reran the airflow, we then apply that to the soiling simulation, but keeping everything else the same. So the only things that's different on this right hand side is we now have the mudguard in this simulation, which you won't be able to see, but just the other side of the bumper here. And we also have the new airflow for this subsequent mudguard simulation. And the images speak for themselves. The image on the left hand side is far greener in colour than the right hand side, and there's even regions that we don't have any coverage at all over the course of the simulation. If we actually look at the numbers, we can see that the instantaneous soiling rates at the worst point for the mudguard simulation is reduced by up to around 10% compared to the baseline state. In the overall soiling, well, we're only ever getting to around 70% occlusion in the 5 seconds of simulation, but what's most important is the rate at which we're increasing is so much lower than that of the baseline state. So overall, we're getting less dirty in the mudguard scenario, and it's taking longer to get dirty, which allows us more time to be able to perform a cleaning cycle so that the LiDAR is able to see at all times. Now, different scenarios are going to affect different LiDARs differently. So in this case, we're looking at the rainfall soiling. Now that's going to affect the front LiDAR far more than it is the rear LiDAR. So maybe what's important is to hypothesize what's going to work for different scenarios, and how do we quantify which scenario is worse for each LiDAR, and then we can optimize during that scenario. Now it's very important to go back and do back checks on other scenarios with the same countermeasures to make sure that we have not optimized ourselves into a corner, and we've created a countermeasure that works perfectly for one scenario but then is detrimental in some other driving condition. Obviously these countermeasures need to be effective at all times for all different scenarios. But if we have something like this rainfall scenario, we have the exact same situation as before, in that we want to monitor where the particles are hitting that surface, how frequently they are, and what the overall soiling rate is and how quickly it becomes fully occluded. So in this case, rainfall is not very heavy, so the overall occlusion is only getting to around 18% in the 5 seconds, so far lower than we were seeing in the previous example. So hopefully that's a clear explanation of how we can monitor what the initial state is of the car, how we can then improve upon that. We're still in the case of there is some level of occlusion and some level of dirtying that is happening. So what do we do once the LiDAR is dirty? Well, this is still something that we're able to do in particle works. So if I just zoom in on this a little bit, what you can see with this LiDAR is that we have a smattering of mud over the surface. So, and then a couple of jets. You can just about see here a little inflow at the bottom here, and I think another one hidden behind this text, which is going to be shooting a jet of fluid onto this surface in order to try to clean it. So if we go and play that video. Now this is just an initial test. We've not done any optimization on this at all, just putting one jet on top, one jet below, and seeing how that performs. And clearly you can see this hasn't done a good enough job. There's still a loss of mud and a loss of fluid in the middle section of this LiDAR, but it allows us to have a base point which we can then iterate on and find an optimal configuration. Potentially it's not even the jets that need to be optimized. Maybe we say that a sphere is just too hard a surface to clean and we need to have a flat plate instead, which is far easier to clean, and we don't have to worry about these curves which are hard to get the fluid around. Regardless, we're still able to get the same data out as before. So what we have in these videos is the occlusion of all of the fluids, that's the mud and the cleaning jets, as well as the mud on its own. So for example, depending on what your sensor is, it might be able to see through clear water, no problem at all. So in that case, we don't need to worry about drops of fluid that remain on the lens after the cleaning cycle is finished. However, some might matter, so we have the water's occlusion as well for where the jet is, and you can see the final state is slightly worse in the all occlusion on the left hand side, just because of those water droplets that we could see that remained on the lens after the cleaning cycle. Again, we can actually monitor that graphically, so starting off at around 15% coverage, we can see that the jet is able to get that down to around maybe 6% of the entire LiDAR is covered, so pretty good for an initial guess. Problem being in the cleaning state is that while the jet is on, we have up to 35-36% coverage for a whole half second. Now, if that does affect the sensor's ability to see, and the clear water and the water is actually occluding the lens itself, well, we want to bring this time as short as possible. So the goal of this optimization is to try to reduce the fluid usage so that we're not having to refill the washer tank as much, but also the time that the cleaning cycle takes, so that we're not having a car that is blind for a whole second while the cleaning is taking place. So overall, to summarise, ParticleWorks is capable of simulating every stage of the soiling process. So that includes the FVM airflow around the vehicle and any subsequent airflows for different driving scenarios and different countermeasures. We can simulate the fluid soiling for any number of different driving conditions, as we've already explained. The countermeasure benchmarking, so we can see how different countermeasures, both passive and active, so we've only looked at a passive feature in this case, but there's no reason why we couldn't use, let's say, an air curtain or a vent that is drawing air and contaminants away from the lens. And so we're able to simulate those different scenarios, create different simulations and benchmark how they perform in comparison to the baseline case. Finally, once we've gone as far as we can with the countermeasures, we need to then optimize on how we need to optimize the cleaning cycles to try to use the least amount of fluid in the least amount of time. What does this allow us to do? Well, the simulation allows OEMs to determine what is the optimal configuration for those active and passive countermeasures in order to reduce the sensor blindness early on in the design process. Overall, the optimization then allows for increased operational range of the vehicle. If we're having to run the jets and the pumps for the jets for long periods of time, it's going to drain the battery of the car and mean that we can drive for less distance. And also, if we're having to use far too much fluid, we have to stop every few miles to refill the washer tank. Obviously not an ideal scenario, but most importantly, the whole reason why we're doing this is to improve the safety of the vehicle so that we can always guarantee that the car is going to be able to see hazards coming and able to ensure the safety of the passengers. So thank you very much. I hope you found this interesting. I will hand back over to Karen now. I think we have some time for a quick Q&A.
Brilliant. Thank you, David, for taking us through today's webinar and helping us understand how particle works can be used to reduce autonomous vehicle sensor blindness. Okay, so before we end, we're just going to move into Q&A, a chance for you to ask any questions that you might have about particle works or any of the other aspects covered in today's webinar. So if you do have a question, please feel free to write it in the side panel that appears on your screen. We'll endeavour to cover as many questions as we can. If we don't get to your question, don't worry. Either myself or my colleague will get back to you after today's webinar. So moving on to the first question, David. Okay, so the first question we have, David, is why is there only fluid on half the car?
Oh, yeah, very good question. This is simply just to save a bit of time. So we're assuming in this case that the soiling is going to be reflected on the other side of the car, and we're just going to cut it in half just to reduce the number of particles. If for whatever reason you did want to do the entire vehicle, maybe you don't have a symmetric car or any other reason that you might like, you simply just extend the domain and create particles on both sides. It'll take a little bit longer to run because there's more particles, but yeah, if that's required, then absolutely we can do it.
Okay, so that leads us nicely on to the next question. A few people have already asked, how long do the simulations take to run?
Bit of a difficult. Well, these ones here, they were all a couple of hours each. So I think the airflow sims maybe an hour or two. The soiling simulations that ran for about 5 seconds, they were, I think, from memory, more like 10 hours or so. So not too long at all. Um, Obviously, the more complicated the simulation, the longer it's going to take to run. So if we were to introduce other vehicles as well, it's a much larger domain, more particles involved. So they're going to take a bit longer to run. So it's a very much it depends answer. I suppose it also depends on the hardware you're running on. If you have a stronger, more powerful hardware, then it's going to take a lot less time. But you're looking into the range of maybe hours, not days, for the most part. And there are ways we can bring it down if required.
Okay, brilliant. So can airflow be run at the same time as a particle simulation?
Okay, yeah. So interesting. The FVM solver that we use today, I use that as a one-way coupling. That means that if I were to introduce the particles at the same time, let me get this right, the airflow affects the particles, but the particles don't affect the airflow. There is also the option to do a two-way coupling. So both the airflow affects the particles and the particles affect the airflow. Each of those obviously is more computationally expensive. So we could have ran a one-way coupling with the airflow and the particles at the same time for pretty much the same computational cost as what you saw today. The one issue with that is right now, when I talked about the scaling the particle size, or the particle mass, I should say, that's not something that can be done with the airflow. That has to be done with an imposed can't be done with the FVM. It's something that can only be done with an imposed airflow afterwards. So we can do it as long as you don't want to do the scale particle mass, but hopefully in future releases, we will also be able to do the FVM with the scale particle mass at the same time.
Okay, thank you very much for that. So another question here is, if we are only making changes to the car, would we also need to rerun the entire simulation, especially if there are other vehicles?
Yeah, no, I suppose what you're asking there is, well, like I just said, it's for a very for a large simulation with, let's say, a couple of lorries in, you need to have such a large domain, and theoretically speaking, anything far away from the car isn't going to be changed if we've added a little mudguard or something. So yeah, so maybe if I share my screen. So let's say, obviously, I've only got one vehicle here and no results, unfortunately, but what I would probably suggest doing, if we had another vehicle here, that's obviously, we need to understand where the particles are coming from. This vehicle that is currently not present, that's going to be changing where the particles are coming from. So we do need to have that information. But what we're able to do is we can include these flow record planes. So
starts off just as a tiny little plane, but let's make it nice and big. I think let's do it. Let's throw in some numbers. So 2 meters. Okay, it's a circle right now, so we can make it a rectangle, and then rotate it about the y-axis, the other direction. What we can do is we can create a box around our car to record anything that's coming into the car. So what we will do here is run our first simulation with no countermeasures, just to understand the baseline soiling. That simulation is going to take a very long time, but if we were to create this box around it using these flow records, what that does is it captures all the information of every particle crossing this boundary, and then allows us to change this in a subsequent simulation to a flow replay. And that replays the simulation just on this level. And what's nice is actually we can then refine the simulation. So if we did this first global simulation quite coarse, we could then rerun this at a much finer resolution, let's say going from 3 millimeters down to 1 millimeters potentially, something like that. And then that just creates the inlets on the on these planes around the car, to then see how the subsequent changes to the car, so a little feature here, mud guards, whatever else we've added on, how that then is affected by the incoming airflow, the incoming particles, I should say, because nothing's going to have changed far away from the vehicle just because we've added something here. So yes, we can keep that little boundary condition exactly the same for all simulations and massively cut down the overall simulation time.
Okay, that answers that question. Right, we have another one here. Would you recommend running on CPU or GPU?
Oh yeah, so Particle Works is heavily optimized for running on GPUs. So we actually did a benchmark, one of my colleagues did a benchmark quite recently, doing a like-for-like comparison of a simulation run in Particle Works on a single GPU. I think the GPU in question was probably an NVIDIA V100, but one of those high-end NVIDIA cards at least. And that was running it equivalent to around 480 cores, CPU cores. So yes, we're looking at, you need a very large cluster to be even comparable to a single GPU, which can fit in a desktop machine. When you also start considering things like the cost of a cluster versus and the cost of a GPU and the cost of enough CPU licenses to run on 480, then we are way ahead if we stick with GPU. So wherever possible, we would always recommend running on GPUs. And we can run on multiple GPUs as well. It's not always required for Particle Works. I know some of our competitor softwares do recommend running on on multiple GPUs at the same time, and that's simply because in order to run as fast as Particle Works, you need to be running on maybe even up to 8 times the amount of hardware. And when each card costs several thousand pounds, it's not an insignificant sum of money.
Okay, thank you. All right, so one question here we've got, has Particle Works being used for wading simulations and water ingress prediction?
Yeah, so hopefully this is a weighted question because you might have seen some of our LinkedIn posts. I think in the past we've done a number of different wading simulation types. So what we've done today is almost like a minor wading simulation, only a few millimeters of water on the road. But yes, we've done a few different types where there is no feedback onto the car. So the car's just driving through a very deep puddle and seeing how that's where the water gets. Again, I think we've used those flow record planes that I just showed before to be able to record the flow into the engine bay and then replay it at a much finer size to see where it goes for the water ingress prediction. There are also capabilities of linking Particle Works with a tool called Recordine, which is a multi-body dynamics tool. And in that way, what we can do is we can read the forces from the fluid onto the vehicle, and then the multi-body tool is able to calculate the resultant motion of the car. So where does it actually cause the vehicle to move up and down because of the forces of the water that it's driving into? Another nice application that some of my colleagues in Italy have done in the past that they've recently done a webinar on was aquaplaning. So, and actually, how do we prevent aquaplaning using features on the car? So this specific application was they had a water jet firing in front of the tyre to try and break up the water on the road in front of the car in order to reduce the risk of aquaplaning. So a number of different applications in that field. I suppose other fields we've not really touched on where else you might use particle works. Forgive me if I'm running over a little bit, but as we've mentioned before, it's mainly any scenario where there's a free surface or splashing elements involved. We've got a lot of thermal capabilities within particle works, so spray cooling for pistons or e-motors these days, lubrication of gearboxes. That's probably the main industrial applications that we use it for, but there's also a number in food and beverage. So I think I saw a nice simulation from some of our colleagues in Italy about sterilization of Parmesan cheese, the big wheels, and basically anything with a spray or splashing elements, you can probably have a go at simulating it.
What I'll do afterwards as well is I'll get back in touch with you and send you some of those case studies and that webinar recording that David's just mentioned. Okay, so just a couple more questions before we run out of time, David. How is the driving speed of the car set?
Okay, yeah, I'll probably go into particle works and show how that's done. So we have this feature called this area called a common script. So this is just a scripting environment where we can define different functions and then call them on the component level. So each component has a keyframes environment where we can either define keyframes time-wise, so we can just say at time 0 be at this location, so on. Sorry, let me just get rid of these. But we can also do scripted keyframes. So in this case, I have a function in my common script called wheel rotation. So I won't go into the maths behind it, but essentially what's going on is wherever wheel rotation is, it's basically working out the rotation of the wheel based off some driving speed, which I've defined at the top here. So in this case, it's defined in kilometers per hour. And all we'll need to do is change that value to something else. Let's try 90 kilometers an hour. And now the speed of the road, the speed of the rotational speed of the tires, and also even the speed at which the fluid is getting injected at, all of those should have now been updated based off that input. So this is a really nice way of trying to keep everything into a single one parameter which defines everything, because it's very easy to forget to change it on your rear tires when if you define everything, I have to go in each one and say, yes, it's now 90 kilometers an hour for the front tire, 90 for the back, 90 for the road, 90 for the inlets. It's very easy to forget one of those. So what we do instead is use the common script so that everything's relating back to this one parameter, and all we have to do is change that and everything updates automatically. Much less scope for error overall.
Thank you. Okay, final question. What advantage does the moving particle simulation method have over SPH for this application?
Yeah, okay. So for this application, well, the first thing is a speed benefit. We usually see is obviously it's slightly dependent on what we're actually simulating, but anywhere from, I don't know, 5 to 10 times as fast simulations using the MPS method compared to SPH. That's mostly down to the stability of the model, because, so I think I mentioned at the start of the webinar how the MPS method was developed for incompressible fluids. The SPH method has been adapted to work for incompressible fluids. So that adaptation means that we need a much smaller time step in order to be able to simulate, to be able to run the simulation in a stable manner. Smaller time step means more calculations. More calculations means it takes longer to run. There's a few other things as well, like the way that we actually discretize solids and fluids. In particle works, we have a very, very efficient way of defining solid boundaries. When in most SPH applications, I believe it needs to be discretized by particles. So again, more particles, more calculations to perform. And often we have to define the air as particles as well. So we can't import an airfield like we've shown today, which is a very inefficient way of running this sort of analysis. Other than speed, I'm not aware. As far as I'm aware, there's no capability in any FPH tools to do the scaled particle size. So as we mentioned before, doing the particle size at the actual 0.6 millimeters would take an incredible amount of time, even in particles, never mind a slower solver. So I believe if that's your idea, you are hoping to simulate these smaller particles, the only way you can actually do it in other tools is to simulate the smaller particles, which is going to take astronomically longer than what we've run today with the 3 millimeter particles. So yeah, I think for this application and for a lot of other applications in this sort of field with the splashing again and the free surfaces, we usually see massive time benefits as well as a few different features that aren't applicable in the other tools that we do have in Particle Works.
Yeah, so it would be interesting to see what is it you're trying to do, and maybe we can have a discussion with you afterwards to see how we might be able to help or answer that a bit further. Sorry everyone, that's all we've got time to cover today. My apologies if we didn't get to your question, but don't worry, either myself or my colleague will get back to you after today's webinar. Before we go, I'd just like to mention that there is a ParticleWorks experience coming up on the 7th to the 8th of June. This is the ParticleWorks user meeting in Italy. It's a brilliant chance to learn more about ParticleWorks, understand how other users are benefiting from the capabilities of ParticleWorks, in addition to how they're using it in their industry and various applications. There will also be training that will be held on site. So if you'd like to find out more, feel free to contact me after today's webinar, but I'll also be sending some additional details out. So thank you, David, again for taking us through today's ParticleWorks webinar. I hope to see you all on the next webinar. Enjoy the rest of your day.